Good afternoon, everyone. Hopefully, everyone had a great day today. My name is Teacher Chi Yew, and I'll be going through the solutions for the P4 competition course first practice over here, which is our daily dose of math organized by Think Academy Singapore. So, without further ado, let's begin on question 1. Now, as shown below, an operation 2 refers to the two numbers with common sides, adding 1 or subtracting 1 at the same time. After a few rounds of operation, the table changes from the left one to the right one. Then the number shown in A should be a particular number. Now, so this really means wherever we try to add a number to a single box, an adjacent box needs to be affected. So in the same way as well. So in this case over here, we can start from the right towards the left because we are always looking for the top left corner, and we want to try to make every single other boxes in this square 2010. So let's take a look how do we work on this. So in this case over here, 1 to 2010, we can say affects the left box operation. In this case, we would have the left box being 2009. In the same fashion, the right side, middle right, 2010, we just need to add 2010 times to the middle box as well, which will result in 2011. Same fashion, going by this logic, we'll get our second column. Now, let's take a look at the second column over here. In the first row, we notice that all we need to do is to really just add one more in order to get 2010. So maybe I'll use blue for the second operation, 2010, but we would like to affect the adjacent side. So we would like to preferably affect the top left corner. So now it's going to become 2 because we added 1 to each of them. In the same fashion, for the middle row, let's take a look at the below row, shall we? So if you want it to become 2010 for the below one, this one must become 2 as well. In the same fashion, for the middle, we want middle to become 2010. So we have to subtract 1 on both sides. So it will be minus 1 now. Now, let's take a look at this a little bit closer. So we are really on track. Our middle column and the right column is all 2010s now. So let's take a look at our bottom left corner. In our bottom left corner now we have 2. We would like to change it into 2010. So this will really mean adding 2008 over here. So 2010 now. So if I add 2008 over here, the top left corner should become 2007. And as a result, if I were to convert the middle left side to 2010, I'll need to add 3. And hence the top left corner will become 5. And therefore, we can conclude that A is equal to 5. Right? Hopefully, everyone is able to get this idea of operations. Is something that's very common in a lot of competition courses. Now, let's move on to question 2, shall we? Now, 4 sets of numbers are shown as below. We have 4 different sets. All 4s, all 5s, all 6s, and all 7s. By adding appropriate signs of operations, that is our addition, subtraction, multiplication, and division, we get the result of 24. Then there are how many sets out of these 4 sets of numbers satisfying these requirements? Now let's take a look at this. So it is really about a little bit more about creativity. How do we manipulate the signs such that we actually get 24? So let's take a look at the first set over here, which is 4 4s. Well, in this case over here, I think it's pretty straightforward. We can see that 4 times 4 is equal to 16. And then all we have left is the other 2 4s. And 16 plus 8 is 24. So that's why all we really need to do is to add the 2 4s and we get 24. Right? So that's our first set. Pretty straightforward. Now what about the second set? Let's take a look at this second set. 4 5s this time. Well, 4 5s might be a little bit more challenging, but you guys see that 5 times 5 is equal to 25, which is pretty close to what we want. Pretty close, but we are still missing a 1. But how do we get that 1? Aha, and that's where division comes in. Right, we realize that 5 divided by 5 is just 1. And hence, we get 24 as well through this set of operations. Well, needless to say, I think what about 4 sixes over here? I think 4 sixes is pretty easy. 4 sixes, we know that 6 plus 6 plus 6 plus 6 is equal to 24. So the third set is clear. Now what about the fourth set? Well, unfortunately, the fourth set is difficult and actually it's impossible for us to actually get 24 on the dot using 4 sevens and all the possible operations. So that's why there are only 3 sets of numbers meeting the requirements over here. Alright, so this one really relies a little bit about creativity, and hopefully you guys are able to be a little bit more creative when it comes to looking at all these numbers in order to solve such questions. Alright, now let's move on to question 3. For 4-digit number ABCD, now if we have ABCD plus AB times CD being a multiple of 1111, what's the smallest value of ABCD? What's the crypto-arithmetic problem over here in this case? Now, so let us take a look carefully at this particular equation. We know that ABCD plus AB times CD is a multiple of 1111. So that's our objective. Now, ABCD plus AB times CD, it looks very complicated. I want to try to simplify it as much as possible. Maybe you will try to make it in terms of just AB and CD only. Right, so let's take a look at how do we do this. We have ABCD plus AB times CD being equal to 100 times of AB. Alright, we are going to split up ABCD into 2 components, plus CD plus AB times CD. Alright, now this is really just equal to, after factorizing, we notice that this is really just equal to AB 100 plus CD plus CD. Now, hey, it doesn't look very factorized yet. Right, we kind of look like we have a common term, which is 100 plus CD, but we do not have the 100 on the other side. Well, in this case over here, teacher Chu has a little trick. All we have to do is to add 100 over here. But compensate and make sure that the equation and the equality doesn't change, we have to compensate by subtracting 100. So this is where the trick comes. And voila, we have 2 sets over here. You guys notice I have 100 plus CD here, and I have 100 plus CD here. But I have to compensate 100. That's the main idea. So let teacher Chu factorize them out. I should have AB plus 1, and then CD plus 100. And then I have to compensate by minusing 100. And what is this equal to? Well, this one is actually equal to 1111k, where k is a natural number that's more than 0. So in this case over here, if we notice, we can actually try to manipulate this equation into something that is much more simple, something that is much more convenient for us to use. Now, let's take a look. Let's look at this a little bit more carefully, shall we? Let's try to iterate through the case this time. And maybe we can try out. Maybe k is equal to 1. What happens when k is equal to 1? Well, when k is equal to 1, right, we get 1111 plus 100 as AB plus 1 times CD plus 100. So over here, we have AB plus 1, CD plus 100 being equal to 1211. Right, but we notice something. We notice a little problem over here. We notice that it's a little bit of a problem over here. Now, why? Because AB plus 1 is equal, this will mean that this must be true. It will be CD divided by 100. Now, this one must definitely be lesser than 12.111. Because assuming that CD is equal to 0. It must definitely be lesser than this amount, because anything larger as a denominator will be a smaller value. Now what would that really mean? This will really mean that AB is equal to 11, or AB is equal to 10. Now, but this is not the case, right? This is not the case, right? Because neither 12 nor 11 are factors of 1, 2, 1, 1. Right. So that is the problem with k is equal to 1. So let teacher Chu use another piece of paper over here right now. Now, so after trying out k is equal to 1 over here, we might want to try out k equal to 2. We can continuously do this. Let's try k equal to 2. Now, we would get, in this case, AB plus 1 and CD plus 100 being equal to 2, 3, 2, 2. Now, which is really just equal to 2 times 3 cubed times 43. After doing some prime factorization. Now, after manipulating a little bit more, we notice that it's pretty nice. We actually get two nice numbers called 18 and 129. So this one will give us a hint. Oh, maybe AB plus 1 is equal to 18. So this one would mean that AB must be equal to 17. And CD plus 100 is equal to 129, implying that CD is equal to 29. Hence, ABCD is equal to 1729. Alright, so I hope everyone is able to understand this. This one is requires a little bit more deep thinking, requires the understanding of factors, be able to solve cryptarithmetic puzzles, etc. So I hope there's a good logical reasoning behind everyone over here, and I hope everyone is able to learn something from this question. Alright, so let's move on to question 4. Now, so Chi Yew plays a card game, alright, that's teacher Chi Yew. Plays a card game including red, yellow, and green cards. Each card has 3 levels, 1 star, 2 star, and 3 star. Now, the 3 lower star cards with the same color can be combined into a higher star card with the same color. A higher star card can be broken down into 2 other lower star cards. So, for example, we have 1 star red can be combined into 2 star red. And 3 star red can be broken down into a 2 star blue and a 2 star yellow. So it's known that Chi Yew can only buy 1 star cards, and they are dispensed randomly, because I of course can buy at least 1 card at a time. In order to ensure that teacher Chi Yew can get 3 different 3 star cards, that is the red 3 star, the yellow 3 star, and the green 3 star, through synthesis or this decomposition operation, then I must buy how many cards? Now this one is a slightly more challenging question. So the slight challenging question over here. So let teacher Chu try to argue and persuade you that the solution is right over here. So let A, B, C represent the number of 1 star, red, yellow, and green cards. Respectively. Now in this case over here, let's take a look at maybe a easier case over here. let's take a look at the case where B, C being equal to 0. How many cards do I need? Well, in this case over here, you guys actually do the calculations. We will definitely need A equal 36 at the minimum. Right, that is essential idea. So what we really require over here is that we require 36 rates. But at the same time, you guys can try it out again. If A 35, B equal 1, C equal 1, alright, works. But A equal 35, B equals 0, C equal to 2 does not work. Aha. So how many cards do we really require actually? If they 5, 0, 2 does not work, and we just need one more card for it to work, the worst case scenario will be we need to have at least 35 plus 0 plus 2 plus 1 equal 38 cards at a time. Alright, so this one is a very abstract question. It focuses a lot on operations, and being able to understand the concept of these two operations and the worst case scenario will greatly benefit students when it comes to answering this question. While this one requires a little bit more thought process, but I hope everyone is able to see that we can consider a smaller worst case scenario first. We can consider the case where the yellow and green cards are 0. How many cards, how many red 1-star cards do we require? And then we start building our logic and idea from there. Alright, so good. I hope everyone is able to understand this question 4. It's a little bit tough. Now, let's take a look at the next question, which is question 5. The side length of a square is integral, right, which is an integer. Now, if the sum of its perimeter and its area is 2021, right, then the side length is something. So, in this case over here, we can let x represent the side length. So, what's the area in this case? The area will just be x squared, right? And what will be the perimeter? The perimeter will just be 4x. Alright? And this one would just be equal to 2021. Well, it looks like we have a quadratic equation over here. But there are times, of course, in primary school, we do not teach quadratic equations, but rather it's only taught in secondary school. We'll be teaching you a few ways, such as a standard rectangular method, completing the square, and maybe a quadratic formula, but we do not do that in primary school. So how do we do this question? Well, in this case, it will make sense for us to try and factorize things out first. We will prime factorize 2021 and factorize the left hand side as well. We get x plus 4 equal 43 times 47. And it seems really clear. We will get x equal 43 as one of our solutions. Right? So clearly, the side length must be equal to 43 in our case. So sometimes when we are not endowed with the formula, we might want to have this kind of creative methods to be able to solve such questions. Alright, so I hope everything is okay. So let us move on to the next question, which is question 6. So let's take a look at this question. A little bit about rates. There are 42 workers who need to complete 1,008 products in total. After they complete half the workload in 3 days, 28 workers left. How many days does it take for the remaining workers to complete the remaining products? Alright, so let teacher Chi Yew use the area over here and talk about question 6. So, of course, let us do a little bit of rates and units idea. This one is a rates and units question now. So let's take a look. We have 1,008 divided by 2, which is 504. This is for 42 workers, right? 3 days. So let's take a look at 1 day then. If we were to calculate 1 day, it will be 504 divided by 3, which is 168, which is 42 workers in 1 day. Now, divided by 42 again, because we have to find the number of workers. How much product would one worker produce in a day? We take 168 divided by 42, we get 4. 1 worker, 1 day. Aha, that's the main idea. So essentially, we are left with 504 products, and then 42 minus 28 equal 14 workers. So each worker needs to produce, because we are dividing our work fairly, assuming that everyone works equal rate, each of them will need to produce 504 divided by 14, which is equal to 36 parts. 36 products. So we require 36 over 4, which is equal to 9 days. Alright, so this is completely everything about rates over here. So 9 days. And I hope everyone is able to understand this pretty clearly. It is something that is taught in a lot of standard syllabus, primary school syllabus. And hopefully you guys are able to add and divide rates, alright, because it's going to be very useful when you move on to secondary school. Now, let's take a look at the last question over here. Uncle Lee has more than 400 rabbits. If 3 rabbits are locked in a cage, there is 1 rabbit in the last cage. If every 5 rabbits are locked in the cage, there are 3 rabbits in the last cage. If every 7 rabbits are locked in the cage, there are 5 rabbits in the last cage. How many rabbits does Uncle Lee have at least? Now, so if you guys notice something, that's the first thing that you must notice over here in this question. For every case that they have shared with us, right, adding 2 will result in all cages having the same number of rabbits. That's the case. You notice that 3 rabbits locked in a cage, we have 1 left. We need 2 more. 5 rabbits locked in a cage, 3 rabbits in the last cage, we need 2 more. 7 rabbits locked in a cage, 5 rabbits left in a cage, we need 2 more as well. So that's the main idea. So this one will give us a kind of idea that maybe, hey, if I were to add 2 to everything, then I'll get a perfect number of rabbits over here. So let us assume that case. If that's the case, we'll probably need to find the lowest common multiple of 3, 5, and 7. And by your ladder method, you guys should know that the lowest common multiple of these 3 numbers is 105. That is essentially the idea. Now, but we know that Uncle Lee has more than 400 rabbits, definitely. So, if I were to have more than 400 rabbits, I'll need to multiply at least by 4 times 4, which is equal to 420. But hey, this is with the assumption that we have 2 more rabbits, because everything is divisible by 3, 5, and 7. So what do we have to do? We have to subtract away the 2 rabbits. Right, so 420 minus 2, and we get 418 rabbits left. And so the final answer will be 418 rabbits at least. So this one, there might be more solutions, but what we are looking at is how many rabbits does Uncle Lee have at least. Alright, so hopefully everyone is able to understand this concept over here about remainders, factors, and prime factorization. So hopefully everyone has enjoyed this set of questions, and definitely keep a lookout for next week's set of questions, and Teacher Chiu will be going through all these the next week's DMD as well. So thank you very much for your time, and I'll see you guys next week again. Alright, bye bye.